Assalamu alaikum. Today we will cover Unit 3 of the course M256 Software Development with Java. Unit 3 Creating a Conceptual Model. As you remember, in Unit 1 we have given an overview of the software development process, and we covered the first phase of this process, which is requirement specifications in Unit 2. Now, and in this unit, we will start to analyze and learn how to analyze the requirements document that we produced in Unit 2, and we will start to structure our proposed system. The unit is titled Creating Conceptual Model, and the conceptual model is just the picture of the system domain as a collection of related conceptual classes. So we will work to identify these classes and identify the relations between these classes. And our conceptual model will be the base to produce more models in what we call the structure of the system. This structure will be improved step by step to be able to produce a full specification of the software that's to be implemented. To be able to build our conceptual model, we need to learn some skills, and these skills will be applied on the requirements document produced for the hospital system in Unit 2. So we will learn the key activities involving in development of a conceptual model. We will learn some techniques to analyze the requirements document produced in Chapter 2, and of course any requirements document. Then we will learn more about the relationships that may exist or can exist between the classes and apply that on our conceptual classes for this system. We will learn about other information that we need to include in the conceptual model. The conceptual model is not only the picture of the conceptual classes in the system. It also includes extra information that we are going to cover today. We'll learn how to derive information from other existing information in the system, and by all this we will be able to build our conceptual model. So now, what do we need specifically to be able to build our conceptual model? We need to identify the real-world entities described in the requirements document. As you remember, the requirements document is taken from the business area, and it used the business language of the real life to describe the system. So we need to identify the most important real world entities in this document. We need to identify the properties of that or these entities, and also the relationships between the entities. All that is taken from the requirements document. We need to identify the limitations imposed in the model, also all taken from the requirements document. The constraints need to be also identified. And at the end, after understanding all these important information about the system, we need to represent that using diagrams and also associated text that will complete the conceptual model, as we will go to see next. It's very important to know that the conceptual model will be the base to create the structure of the software. It will identify the classes that will make up the system. And of course, the classes will produce for us the objects that will interact within the system to perform the system tasks. A fact that you need to remember always that the conceptual model gives rise to the initial structure model. And the initial structure model will help building the implementation model, which is our main delivery of the design phase. The slides shows the relations between the different models. As you can see, you get the information from the user to get the requirements specifications that will come out as requirements document. We'll use the requirements document to build the conceptual model and the initial structure model. The initial structure model will go into developing the dynamic models, and the diagram shows the chapters involved in all this process. We start with the classes, very important concept in object-oriented programming, and after all what we are doing is object-oriented software development. A class in our development represents some real-world entity, and objects are instantiated from these classes. To be able to complete building the class, we need to find out what are the attributes of this class objects. And we know that for each attribute of an object, there is a value. So if we assume that the object is a student, then the student has an attribute, for example, first name, and that need to have a value. For example, Ahmed is a value for the attribute name of the object student from the class student. Now in the real life, objects are related, and through these relations they interact, and that's how our real life goes on. Our real life goes on by the actual interaction between the objects. These relationships between the objects and the real-world entities need to be mapped to relationships between the class models so that the objects in the system can have the chance to interact. When there's a link or a relation between one object and another, this relation is called association in software development. And as the object is an instantiation of a class, the link between two objects is just an instantiation of an association. So in real life, how do we identify objects? We look around, and from our experience, we can distinguish one object from the other. And we call these things things. Now, to be able to identify the classes in software development, we have the system domain given in the requirements document, and we need to look for things in the system domain. So we basically on nouns and noun phrases. So every noun and noun phrase is a candidate to be a class in our system. And this process is called textual analysis. If you take an example of a system domain, what we need to do to be able to identify classes is to look for nouns and noun phrases and take them as candidates to be classes in our system. Here we don't mean that every noun and noun phrase is a class. No, every noun or noun phrase is a candidate to be a class. We will learn how to identify our classes and reject the irrelevant classes in our text. Here's an example of the system domain for a library or a DVD library. As you can see from this slide, all nouns and noun phrases are underlined. So all nouns and noun phrases are candidates to be classes in this system. You can easily see that some of the nouns or noun phrases are repeated. For example, if you take DVD, you find it in more than one place, or film, or loan. So we'll take a copy of each one of them and we will continue working on these to be able to identify our classes. Now we take the list of all the identified nouns and noun phrases and we list them as candidates to be classes in our system. As you can see, we didn't repeat the same names again. So if we have a DVD or film, we list it once here. There's also a few things that we need to note regarding this slide. First, we don't use only singular noun or noun phrases, because at the end, our class must always be singular. In the system domain, DVD, which is a physical video disc, is synonymous for or with copy. As you know, copies of the film are held on DVDs. But also, you may find copies of films held on videotape, for example. We need here to distinguish between the DVD as tangible thing and the film itself as intangible things. So you may have many DVDs of the single film on the library. So many DVDs for the same film may exist in the library. Now, as we mentioned earlier, not all these classes in the list are classes in our system. Some of them are not, and we need to learn how to reject the irrelevant classes. Our guidelines for rejecting of candidate classes. The first one is the candidate class identified an attribute? Does it correspond to some simple property of some other category of objects in the application area? Like, for example, title is an attribute of a film. It's not a class that I need to build. Return date, for example, is an attribute of loan. I don't need to create an object or a class called return date, and so on. If the candidate class refers to some behavior of the system, then I reject it. For example, take a list, which represents the list of film titles. So this list is not significant for the system domain itself. It's just something that the system needs to produce as part of its behavior. So if it's an attribute, then I reject it. If it refers to a behavior of the system, then I reject it. The third point, if the noun or the noun phrase is out of the scope of the system, then I reject it. So the noun library falls in this category. The whole system that I'm building is a library. I'm not going to build a class called library. So this kind of phrases or words will help me describing the general purpose of the system. It's not meant to be a class in the system. Fourth guideline to reject candidate classes is if the noun or the noun phrase refer to an aspect of the user interface. For example, we have the candidate class barcode reader. This is actually part of the interface in the library, and some tangible physical thing in the library. It's not part of my system, but part of my system interface. So I reject it as a candidate class in my system. Is it some language idiom? Just part of general English usage, like for example the fact that, number of. This is just language phrases that we use to describe things. So it's not part of my system. I don't need to implement these nouns and noun phrases as classes in my system. Now, does the noun or noun phrase refer to connections between significant entities in the system domain? If it's so, then we will find out whether we can reject it or we may need to build it as a class. If that noun or noun phrase is very important to connect both classes in the system domain and it had no properties, then it may be more appropriate to model it as association. Is the word or phrase that's used in talking about the system in general, or rather than reference to something in the system domain, something like we say system, behavior, requirement. These are not entities, these are just words that we use and phrases that we use to describe the system in general. Now, after applying all these guidelines to reject the candidate classes and keep only the significant ones, and when applying these guidelines on the system domain of a DVD library given in this slide, we have only 4 classes left, which are DVD, film, member, and loan. As we mentioned earlier, we always use singular nouns for class names. When we have 2 words in the class name, we capitalize the first letter of each word. So now, after identifying our classes, and for cross-checking, we may find some particular kind of classes in our list. First category is tangible entities, which are physical things in the world of the system domain, such as people, vehicles, and things that you can see and touch. Some classes in the class domain, in the system domain, can be roles, which are played by people, such as student, policeman, employee, driver. And in the real life, people may change their roles, and this possibly can be also in the system domain. The third type of classes is the events, like for example booking, reserving, registering, and so on. More classes can be of organizational units, like for example department, faculty, branch. And the last type of classes, which is also very common, are abstract entities, like piece of music, novel, and things. These correspond to intangible entities. Now, to categorize our identified classes in the DVD library, we identified 4 classes: DVD, member, film, and loan. We find that DVD is a tangible entity where member comes under the role kind of classes, film is an abstract entity class, and loan is an event. Now we'll go back to the domain or system domain of a DVD library to identify the attributes of these classes. We'll based on nouns and noun phrases to identify these attributes. And as you remember, we rejected some of these nouns and noun phrases because they are attributes of some of these classes. If you go back to the system domain of our DVD library, we may find that the film class, for example, has attributes such as title and number available. DVD has an attribute number. Member has attribute number and name. Loan has the attribute return date and issue date. As we mentioned earlier, we instantiate objects from a class, and we instantiate links from associations. So association is a link between two classes, and at the running time of the system, it will represent a link between two objects. This link is very essential and very important for the two objects to communicate and interact and cooperate. For example, in the DVD library system, each film object may be linked to a number of DVD objects, and this represents the association between the object film and the object DVD. And as you can see in the object diagram illustrated on the right, we have film 1 linked to DVD 1, 2, and 3, and another object diagram showing film 2 linked to DVD 4 and DVD 5. So in the class diagram, we'll have one film class associated to one DVD class. At the object level, this association will be instantiated to create links between number of objects from the film side to number of objects from the DVD side. As with the case of classes and attributes, we give names for associations, and that name of an association should be a single word and give us an indication of the meaning of that association. In the conventions, the association name starts with lowercase, just like the case of attributes. Sometimes the association name may not help you an idea or give you an idea about the direction of the association. So you need to read the association name in both directions to be able to identify the relation direction. How to identify these associations? We can go back to our system domain, and from the system domain you will be able to identify the associations between the objects, which will be representing the associations between the classes. So when you read in the system domain, you find that the system domain is trying to relate objects to each other or classes to each other, and from there you can identify these associations. Here is the underlines showing the possible associations between classes. So classes appear in bold text, and you can see, for example, DVDs of a number of films. There's a relation between DVD and films. Library member can borrow a DVD of a film. So you can see that, or text with underline represents a candidate association between classes. Now we bring them and find that clearly the system domain give us an idea about the associations and links between classes and objects. So we can draw some of them, as you can see in the diagram below. Member borrows DVD. So borrows is the association between the class member and the class DVD, and in the implementation level you find one member may borrow more than one DVD. More associations identified in our system, and you find all our 4 classes member, loan, DVD, film are connected now, and a well-named association is used to connect them. Now, in this diagram, which is a class diagram, we know that member is connected to loan, but how many members connected to how many loans? We have no idea, and the diagram doesn't tell us anything about this. So now we will add more information to the class diagram to decide about how many objects from one side is connected to how many objects from the other side. And that's what we call multiplicity. We use some particular format to show that the allowed number of objects to be created from this class is specified. For example, in this object diagram, you find that member 2 has no loans at all, where member 3 is having 1 loan, member 1 is having 3 loans. So we need to decide about what are the number of allowed objects to be instantiated in different situations. In this diagram, as you can see, there's a number 1 next to the tutor class and number 20 next to the student class. Means in this system I can create only 1 tutor object, but I can create up to 20 student objects. And there's more than one format to express multiplicity. We can use exact number, like for example 1, as we have seen in the previous slide, means 1 tutor, or exact number 20. We can use a range of number, meaning I can create from 0 to 6 objects, or from 0 to 1. And we have also a very common use multiplicity is from 0 and open to any number. Now we have added the multiplicities to our class diagram, and now we know what is the number of objects are allowed to be created by each and every class in our diagram. So we know that one member can take from 0 to 6 loans, and a DVD can be on 0 or 1 alone, where a film can be or can appear on 0 or open number of DVDs. The DVD library system, the system domain was small, the number of classes was small also, so we use it to start learning how to do the textual analysis and identify our classes, identify our attributes for these classes, identify associations, and building the conceptual diagram as we have seen in the previous slides. Now we will apply the same rules on our system, the hospital system. In this slide you see the system domain of the hospital system, and you can see that all the nouns and noun phrases are underlined. We are going through the same process again with a bigger system domain and try to identify the classes in the hospital system. As we have done with the DVD library system, we have the list of all the candidate classes in this system, and we need to apply the rejection guidelines to reject the irrelevant classes and keep only the relevant ones. Here is detailed of all the classes, and we find on the right reasons for rejecting these classes. For example, hospital is outside the scope of the system. Type or name is an attribute of word. Team code, attribute of a team, and so on. After going through the process, only the following classes are kept and the others all rejected. We identified the classes ward, patient, doctor, team, consultant doctor, and junior doctor. As we have done with the DVD library, we will identify the attributes of the classes, and we identified from the system domain that the word has the name, type, capacity, number of free beds. Patient has name, sex, date of birth, and age. Doctor has name, team has team code, junior doctor has name and grade, and consultant doctor has name, attribute. Now we put the classes in more informative format. We called it the class description. And you can see that class description will include class name and a description of what does this name mean, a ward in a hospital. Ward is a ward in a hospital. Then its attributes identified in the previous slides, name, type, capacity, and number of beds, and a description of every attribute identified. So name, the unique name of a ward. Type, whether the ward is for male or female patients, and so on. So now we go back to our classes identified in the system and provide class description for every one of them, including the class name and describing it, and the attributes, and giving an idea about what does this attribute represents. More on class descriptions: team, doctor, junior doctor, and consultant doctor. Now, same as for DVD library system earlier, we define and identify different kind of association in the system. one of the common and important associations in object-oriented paradigm is the Generalization Association. If we found an umbrella for more than one class, then we may have what we call a generalized class to represent these classes. For example, we know that the junior doctor and the consultant doctor are both doctors. So the doctor entity, doctor class, can represent both junior and consultant doctor, which means that class doctor generalizes each of the classes junior doctor and consultant doctor. And in object-oriented programming, we call doctor a superclass for the subclasses junior doctor and consultant doctor. Or in some situations, we call it a parent class for those two classes. And this diagram, we show possible representations for the generalization relationship in UML. Both representations are correct, and we say that junior doctor inherits doctor and consultant doctor inherits doctor class. And we need to make this very clear in the description of the classes. So we say class doctor, a doctor at hospital, and the class generalizes junior doctor and consultant doctor. And as you can see, we have a name attribute for doctor class, but we don't have a name attribute for junior doctor or consultant doctor class. Why? Because junior doctor class and consultant doctor class will inherit this attribute from their superclass doctor. Now it's also useful to revise with you the concept of abstract classes. As you may know, and you for sure covered in M257, any class that has no instance of its own but only instance of its child classes is called abstract class. Okay, so in the hospital system, any doctor in the system or in the hospital is either a junior doctor or a consultant doctor. So the superclass doctor has no objects or instances of its own. Any doctor can be either under the consultant doctor or the junior doctor class. We use those classes to define the properties common in both classes. So for example, instead of defining a name for a consultant doctor and a name for junior doctor, I will declare a name in the superclass doctor, and both classes will inherit that name. In case of having our abstract class in our system, we add abstract to the name of the class, as you can see in the figure below. Doctor class is an abstract class. If the class has no abstract with its name in the class diagram, then we call this class concrete class, which is a class that can create object of its own. Now, as we have done with the DVD library system, we need to go back to the system domain of the hospital system and identify the associations between our identified classes. Going through the same procedure, you can identify the following associations between the hospital system classes. For example, team cares for patient, team contains doctors, and so on. Now, this conceptual class diagram or class diagram has no multiplicities. I have no idea about how many teams are caring for how many patients, no idea how many doctors are in a team, and so on. So to complete the class diagram, I need also to decide about the multiplicities in the diagram. Again, as I mentioned earlier, generalization is just an association, like other associations identified earlier. So I need to add them to the class diagram, and also I need to add the multiplicities to the class diagram. Now if you look at the diagram, you find that now I know how many objects from one side is connected or can be connected to how many objects from the other side on my associations. If you look at the generalization relationship, you don't find any multiplicities. Why? Because every junior doctor is a doctor and every consultant doctor is a doctor. There is no limit for the number of objects created according to this relationship. And in this slide and the following one, we explain why we have chosen these multiplicities for the hospital system classes. Now, a very important part of building the conceptual diagram is to decide whether I want to take an event as a class or as an association. What's an event first? An event is any significant circumstance, episode, interaction, happening, or an incident in the system domain. For example, registration in the university system, booking in the hotel system, enrollment, reservation in the library system. All these we call them events. So, are we going to represent these events as classes in our system or as associations in our system? The basic rule is that if there are other additional information to be associated with the event, then we may need to represent it as a class. If no additional information is required, then we may represent it as association. In this example, we have the event loan. And as you can see in the object diagram, the object in the middle, loan 2, needs extra information about the loan, like issue date and return date. As we mentioned earlier, if we need more information and additional information, then we have to represent it as a class, and that's what we have done in the DVD library system. We represent the loan as a class in the system because additional information is needed. Where in the example of in the system of hospital system, we have treatment as an event, but as we have no additional information required by treatment, we decided to represent it as an association. So Dr. 3 treats patient 5, and this is represented as an association. In case, for example, we found that treatment is acquiring additional information, then we may need to represent it as a class. And in this diagram, we see treatment represented as a class, and we see an object diagram of treatment. But in our hospital system, we have no additional information required for treatment. For example, how many times it can be, when it is done, and so on. And since this additional information is not needed, so we don't represent it in the hospital system as a class, we just represent it as an association. In summary, we try to ask the following questions and decide about whether we are going to represent the event as a class or as an association. First question is, does the event have any properties whose value need to be recorded? Then we need to record them within a class. Does the event involve more than two other significance entities? Do different occurrences of the event involving the same entity need to be recorded? In all these cases, you find that additional information is needed and the event is need to be presented as a class. Otherwise, we will represent the event as association only. The following slides you find exercises that will help you deepen the understanding of how to model events, whether using classes or using associations only. One more attribute that need to be added to the conceptual model is what we call the invariants. The invariants are conditions on the objects of conceptual model, or conditions on the attribute of these objects. We need to satisfy this condition to guarantee building the right conceptual diagram. So they are kind of constraints on the real world entities. To illustrate this, we'll have a look at some of the invariants in the hospital system. For example, consider the following extracts from the hospital system. It says the system displays for each such junior doctor their grades 1, 2, or 3. So this constraint on the junior doctor object can be represented as follows. The grade attribute of a junior doctor object has value which is either 1, 2, or 3. So we put a constraint condition on the grade attribute, and it can be only 1, 2, or 3. This is an invariant on the attribute grade of the class junior doctor. Another example is the requirements document for the hospital system says each ward has a unique name and each team has a unique team code. These are invariants on those classes attributes, the name of a ward and the team code of a team, that they need to be unique. More examples of invariants. For example, if you take this requirement from the requirements document, it says that each patient is under a care of a single team of doctors. So the entity patient is under the condition that it must be linked to one team object. It cannot be linked to more than one team object, and it cannot be left without being linked to a team object. All these are examples of invariants that we need to hold so the system can be stable. These invariants can be on the relations between the links, as we can see in this slide and in the following slide. So even we can have invariants on the links between the objects. They also can be conditions on relationships between links, relationships between attributes, values, and links, as we see in these examples. Not all attributes and associations are given obviously in the system domain. By deep understanding of the system domain, we can derive attributes and associations. What do we mean by deriving them? Means that we can produce attributes from some existing attributes or associations from some existing associations. For example, if we know the date of birth of a patient in the hospital system, then we can work out the value of the patient's age attribute. By this we say that we can derive the age attribute from the date of birth attribute. Derived attribute is an attribute whose value can be deduced from other elements of the model. And in UML, the derived attribute indicated by preceding their names with a slash, as we are going to see in the following diagrams. Associations also can be derived from available associations. In this example and in this class diagram, we know that team is headed by a consultant doctor, and team, including all doctors in that team, cares for a patient. And in the system domain, it says that the consultant doctor is responsible for the patient. So even if the relationship is responsible for is not there, we know that the consultant doctor, who is the head of the team, is actually cares for that patient because he is a member of the team. But since the consultant doctor is heading the team, then he is responsible for all the patients on that team. So this relation can be derived, means the is responsible for relation can be derived from the cares for relation, because after all, the consultant doctor is a member in the team that cares for the patient. That's why in this diagram we put a slash preceding the is responsible for association name to say that this is a derived association. Now, after going through these processes of building the conceptual model for the hospital system, we show the complete conceptual model for the hospital system. It will include class, diagram, associated text, and invariants. The class diagram includes the classes that have been identified, all associations and generalization relationships, abstract classes, derived associations, and derived attributes. The diagram is not the conceptual diagram. The diagram is part of the conceptual model. So the conceptual model includes other things than class diagram. You need to remember this very well. Conceptual model includes classes, text descriptions, and invariants. So this is part of the conceptual model, which is the class diagram, including all its associations and multiplicities. To complete the conceptual model, we need to add description of all classes appearing in the conceptual diagram, and also invariants on the objects of the conceptual diagram. So to say that I have a complete conceptual diagram, I need to have the invariants, the class descriptions, besides the class diagram or the conceptual diagram of the system. This is the end of Unit 3. You need to practice what we have learned today: textual analysis, identifying classes, identifying relations between classes, identifying attributes of the classes, building the conceptual class model, adding the multiplicities for that model, then describing the individual classes, building the list of invariants on these objects, and also deriving attributes and deriving association. Thank you very much. Wassalamu alaikum wa rahmatullah wa barakatuh.